right. Hello, everyone. How are we all doing? Good?
Good, yeah.
Nice. I hope everyone's had a good conference so far. I know I have. Welcome, and thank you for joining our talk, From Trees to Transformers, our journey towards deep learning for ranking. The talk itself will take around 30 minutes, give or take, so there should be plenty of time for questions at the end, which is usually the more interesting part anyways. So, My name is Mihail. I'm a senior data scientist at GetYourGuide.
Hi, I'm Theo. I'm a data science manager at GetYourGuide.
And today we're gonna talk about how our team at GetYourGuide adopted deep learning for ranking activities in our marketplace. So for the agenda today, I'll start off by giving a bit of context first about what GetYourGuide sort of is and why ranking is important for us. Then I'll briefly introduce the learning to rank sort of framework and how it can be used to build machine learning models for recommender and ranking systems. Then Theo will talk about how the state of our ranking system roughly about a year ago, and what sort of motivated us to move to deep learning, and how we kind of approached this migration when it came to experimentation, and kind of what were the challenges and learnings along that way. And in the end, we'll wrap up with an overview of the kind of two experiments that really worked well for us, the kind of winners, let's call them, including a deep dive into the model architecture itself and sort of the key takeaways from this journey. Maybe, so anyone who's familiar with GetYourGuide from before? Okay, wow, that's pretty good. There's a few hands. But those who are not familiar, GetYourGuide is an online marketplace for discovering and booking experiences for travel. And the way we operate, we're a two-sided marketplace. So we have essentially two types of users. On one hand, we have the suppliers, we call them. These are the actual operators of the activities. For example, a walking tour operator in London. So they're kind of small businesses that come to GetYourGuide to list their activities online. And then on the other side, we have the travelers who are looking for things to do for their next trip. And today we have over 100,000 activities online with millions of people using the platform. So with this scale, sort of matching the travelers to the activities is very important. And that's where ranking can really help us. So every time there is a request coming in for to look for things to do at a specific location, there is a two-step process that sort of takes place. The first one is the retrieval, which means we're sort of fetching a very broad set of search results. So again, these are activities. For example, based on whether the specific activity is tagged to the location that the user is looking for. So in this case, we have one user looking for things to do in Barcelona, and we've retrieved 809 activities tagged to that location. I'm not sure if you can read it very well, but there it is. And the second step after the retrieval, we have the ranking step. So this is all about sort of optimizing those retrieved search results to kind of maximize the relevance for the user. Because if we can do that really well, that means there's a higher chance that they find something they're interested in, and sort of we maximize the chances of conversion, which is good for us, but also our partners, the suppliers, generating revenue for them. So the thing is, today, screen sizes and kind of user attention is very limited, which kind of implies the top positions on a landing page are inherently more valuable. So we really kind of want to nail down this ranking and make sure we're doing a good job there. And there's, of course, many factors to consider here. For instance, what are the seasonal patterns for a location? Maybe some activities are more important or more relevant in the summer versus the winter. What is the user locale? Do they have certain constraints when it comes to the conduction language of the tour, for example, or the activity? What is the historical performance? Has the activity performed really well in the past? If so, that probably means it's more relevant. And of course, we're all individuals, so while this user might be interested in kind of the architecture and museums in the city, there might be another user who's more into outdoor and kind of nature activities. So it makes sense for the landing pages of Barcelona, again, to sort of look different and for these people. So how do we go about solving this sort of thing? And over the last kind of better part of the 2 decades almost, I would say, the learning to rank framework has kind of emerged as the de facto approach. And it essentially kind of boils down to using historical search queries from real users to then determine which items were relevant to them, and then train a model, a machine learning model on that data. So as users come to our platform and look for things to do, they submit a search query, maybe some filters to go along with that query. And then we, when I say we, I mean the ranking team or the ranking service, we return a list of results that are to be displayed on a landing page to the user. And of course, as users view these landing pages, they usually tend to interact with some of the content, some of the activities included there. So clicking on an activity, maybe reading some descriptions, and maybe even booking something. And it is these user actions that kind of tell us what in the end ended up being relevant to the user. So we're using it as a sort of implicit user feedback to determine the relevance of the item. So then after those user actions, so each user action essentially creates an event that we log into our data warehouse. And we can then process those events, join the historical search queries, so the total list of items that were displayed to the user, and join them with the user actions, so what they end up viewing and maybe booking. And then, aggregate that data and sort of train a new machine learning model on that, where, and after that is done, we kind of publish it to a model registry where it can then be picked up again by the ranking service to be used for serving new queries. So this is sort of the general workflow. We do this every day, essentially, because user interest can change over time. There's different trends, so we want to make sure that we're always kind of up to date with that. But as with any sort of production machine learning system, before we kind of deploy anything or even think about running any A/B test, we kind of want to make sure that the model that we just trained sort of works or have some confidence. So we want to do that offline before any deployment. So in other words, we need to evaluate our model. So how does that look like? I think a lot of you are surely familiar with like classification and regression problems, but how do we evaluate a ranking model? And there's actually many ways to do that. But sort of one of the most common and pretty straightforward methods is a metric called average precision. And to compute this metric, the first step is to, again, determine which items were relevant to the user. So a binary label, 0 if it was not relevant, 1 if it was. And to do this, again, we fall back to the user actions that they took after a search result was shown to them. So the clicks and the bookings, these could be used to determine this binary relevance. And then essentially, we compute the precision of the search results at different positions k, shown here. And then, so the precision would be the share of relevant results in the first k results. And then we take the average of those different values, so the different precisions at k, and that gives us our relevance metric. So the great thing is we can train a model and then compute this metric offline. We compare that to, we compare the value of the new model, the new performance, to the control model offline, and then maybe we get some confidence to then try out an A/B test. So at this point, I'll hand it over to Theo to give a bit more details of sort of what our modeling stack looked like and why we decided to move to deep learning.
Great. Hi. So now let's dive into the ML model. And for that, think on the top here, what I will be focusing on is this machine learning model, which is part of the ranking service. And so for that, we get in this model, we get the query and the activity, and then we need to combine it first with the activity features. And from that, we get them from an in-memory database. And we also want to combine this information with some information that we have from the traveler, or what the past interaction we have with him. So for that, we go to our feature store, and all of this information are combined, and then we put everything into our scikit-learn pipeline. So, and this scikit-learn pipeline is kind of broken down into two parts. The first part, a pre-processing, where we use transformers and on pandas data frame to prepare the features to be ready for the model. And then we have our predictor, which is an XGBoost ranker, so which use exactly the learning to rank that Mihail presented just before. And now the focus here basically is on changing this model in this part. But you might be asking, why first, right? Why moving to deep learning? So we had three main reasons. The first one, actually, we start seeing diminishing return on our tree-based approaches. So we felt we were kind of reaching the limit of what was possible with this framework. Second, we see that deep learning offers much more flexibility, especially in terms of model architecture, being able to customize the loss. We can exploit much bigger data set, and also for the feature, there are also much more flexibility in terms of handling categorical feature, being able to incorporate text and images. Then the third one is we saw that also external validation. So when we look at industry case studies, we saw that other marketplaces like Airbnb, Wayfair, Etsy moved to deep learning and claimed that it was transformative for them. So sounds easy, right? We just throw deep learning, throw some GPU at it, NVIDIA will be very happy. Actually, was a bit more complicated than that. A bit more seriously, basically, we had some expectation by reading the different company blog posts and talking with others that went through this. We expected a complex and long process. That was pretty clear from the different shared experience. And that's actually, in reality, yeah, that was true. It took more than 6 months to get there. We were a bit, we know that will be some unknown infrastructure, and we might be needed to invest, in particular in terms of the training time. And that was the case, actually. The training time over deep learning is much longer than XGBoost. And so for that, we had to tweak our CI to be able to still being able to run in a reasonable time. Also, working with GPUs, we were a bit afraid of that. Actually, training on a GPU was relatively straightforward on Databricks. However, training with multiple GPUs, we got into some nitty-gritty details of making it fail, especially with the embedding. When you put the max norm, then suddenly the multi-GPU breaks. Good luck to figure this out by yourself. It took us some time. And also the inference of a deep learning. Yes, we also had some struggle at start. We had to set some specific parameter on the Torch CPU, set num threads. And also we saw something more recently that the memory usage, because the model is taking bigger, and the memory usage and the latency are kind of related. So if we increase the memory, we actually reduce the latency, even if before we still were in a healthy zone in terms of memory usage for our pods. So this kind of weird thing here. But what we were the most afraid of is the thing we didn't know about and we'll discover on the road. And actually, we got one of them is actually just one. I'm pretty happy about that, but the Docker image. just blew up in size with PyTorch with all the compilation, and that created problem because our CI was running out of memory. That's something, but something we couldn't handle with relatively with some effort, basically. Great. So here is what we have, what we expected, and what's the reality. And now I will explain a bit more how we broke it down, this big project, this more than 6 months project, to be able to adopt. And what we did actually is to have different milestones. And the first one that we had for Q2 of last year was to say, okay, we've first tried to get technical parity between our tree-based model and our deep learning model. So that means, in particular, being able to handle the throughputs and the latency requirement that we have. And we started very simple with a minimal hackable network. So we spent 2 days in the team focusing with pair programming, everyone, me included. And what we got out of it is a hacky neural network, which was just trained on 4 features instead of the more than 40 that we have. But we were able to deploy it and put it behind a feature toggle, which means that it was part of the live service, but it was not exposed to any users. But for them, we could get some testing, and then we could get a first model, the minimal viable network. So here what we had is a basic architecture, just a few fully connected layers, but we were able to use all the features. We got some okay-ish ranking metrics, not great, but that was not the goal at this point. And we could not yet optimize for all our business goal. However, we still wanted to launch it as an A/B test for learning purposes, more on the technical level. So which means here that what we did is 50% of the visitors that got to our website then got a ranking that was based off this new deep learning model, and the other half would still have the tree base. And then we can compare what kind of differences you have in terms of business metrics, ranking metrics, etc. And then we finally was able to launch our minimal lovable network. And there we had the business objective parity. We also complete all the technical requirements in terms of throughput, latency. We were fine. So we achieved our first milestone at the end of Q2. We are very happy. And we decided that we can move to our next milestone, which will be business parity. So in Q3, we actually aim to move toward the business parity, which means have the same business performance as our tree-based model. And what we start doing is actually exploring new architecture. So we saw that actually getting a transformer architecture where using self-attention on the different between the different activities give a big improvement in our ranking metrics. So very exciting. We tested it in the A/B test, but actually what we saw, even if our ranking metric improved, we saw more people bouncing on our website. So we had people that just come on the website, and on the B side with this model, they didn't interact with anything and just left. So what we then got back to together, and we then got to the clickbait transformer. So here, what we did, we reused the same architecture, and to account for bouncing, we also added data of visitors who click on some activity and not just bookings as we had before. There we got actually flat business results, and so we were happy we achieved our second milestone. And now we get to Q4, and we say, now we are ready to outperform. And actually, took us some time. So we got 4 more experiments until we get our first win. And our first win was the category conversar transformer. So what we added actually is adding the semantic similarity between the activity and the category of the page. Like think of category like wine tasting in France, or monk meditation in Japan. This, for us, are all categories. And we saw an uplift in the ranking metrics, but more importantly, we also saw uplift in the number of bookings. And it was just before Christmas. There was a small Christmas gift from the god of A/B experiments. And yeah, in practice, basically, to make it more visual, so we have the category. So I'm French, as you can see here from my accent. So croissant, baguette, and pastry is a very important category for us, for me at least. And then you can combine it. You have a semantic embedding of it, and you can also look at the text of the activity. And from those, you can get a kind of similarity between the two. And that was then fed to our model. But then in Q1 this year, actually, we got our biggest win from the last years. And for that, what we start experimenting with even new architecture, and then we start adding deep and cross neural network, and we added trainable embeddings, and we also increased the size of the data set. And we got like a very clear win in our ranking metrics by 2.2, which was bigger than what we had in the last few years in our tree-based. And also same with our, in terms of business impact. So in terms of bookings and revenue. And with that, I will give it back to Mihail, who will go in deep dive into the specific of this model.
All right, so yeah, I guess probably a lot of you are wondering at this stage, so what does the model look like? So here's kind of a rough sketch. To break it down a bit, the ranking model that we kind of have, this is pretty close to what we would have today as well. Consists of two sort of main components, the deep and cross network, and then the ranking transformer at the very top. So this shows mostly the deep and cross network. And here it all starts with the embedding layer, where we kind of transform sparse features into dense representations. So you might be familiar with embeddings in the context of like words or natural language processing. So in our case, sparse features can be any categorical variable. So for example, the user's locale, that could be one. But also we do embed the specific entities. So the IDs, the unique identifiers for an activity or a location that is included in the request. So we're generating a unique embedding for the items, the entities to be ranked. So after we generate the embeddings, we also concatenate those embeddings with any dense feature that we have. So for example, the historical click-through rate of particular activity, that would be just a typical numeric kind of feature. So those types of features are concatenated to the same vector. And then that vector is passed along into two kind of parallel subnetworks. So on the left here, we have the deep network. So this is pretty much your very standard kind of fully connected network with some nonlinearities. So in our case, that is the rectified linear unit, so the ReLU activation. And the task of this kind of subnetwork is to generate sort of higher dimensional and like very nonlinear representations or features for the individual activities that are part of a single like ranking request. And then on the right, we have the cross network. So the task of the cross network is to apply like very explicit linear feature crossings. So using that formula over there at the bottom. So traditional fully connected network with kind of nonlinear activations are usually not very efficient into like modeling this explicit feature interactions or feature crossings. So what is a feature crossing? Let's say a particular request is for a category called pub tour, and we know that the user is looking for a place like London. So the crossing would be a simple AND statement. So a category is pub tour and the location is London. That's probably a good signal for the ranking model then. So that is an explicit kind of feature crossing of the second degree. So you can kind of expand the network. So the more layers you have, then you have more degrees of crossings. So then after the two networks have processed the kind of input, the outputs of those two are concatenated again together and passed along to the ranking transformer, so which is the second kind of main component of a ranking model. And yeah, so the ranking transformer, this is obviously inspired by the traditional, or like the original transformer architecture from attention is all you need. I'm not going to go too much into the detail here because there's been a couple talks already, like very good talks, and I think there's one later today that really go into the internals of this thing. But kind of the summary here is that we have 2 encoder blocks. So each of those encoder blocks has a like 3 self-attention heads. So it's a 3-headed self-attention, followed by a feed-forward network and some skip connections and layer norms in between. So that's kind of roughly it. Maybe one thing to kind of highlight here, excuse me, is that we don't use positional encoding. So transformers, typically when they're applied to like word or like text, the kind of order of the words, let's say, so the order of the input is very relevant, obviously. But in our case, the ordering of the inputs is not really that meaningful. We do care about the order of the output, so that what we end up showing to the user, so the ranking is very important. So the output is important, but the input is not, we don't care really about that as much. So we don't use any positional encoding. And then, at the end, we have, the linear layer that just outputs a score, a relevant score with which we then kind of order the contents or the items. And the idea here is, so previously we showed the deep and cross network. That kind of main idea there is that we generate these nonlinear features and the explicit feature crossings, so the features for the individual items, so kind of representations of the activities, let's say. But the task of the transformer is actually to apply the self-attention mechanism to the entirety of the query. So kind of looking at the query in a more holistic way. So for example, let's say we're ranking 8 results for one page, and 7 of them are walking tours, and 1 is a food tour. Looking at that whole query holistically, then you can imagine that the relative importance of the food tour is more important than the single walking tour. So that's the idea. We apply the self-attention to the whole thing. And so at this stage, I'm going to pass it back to Theo to talk about the key takeaways and the lessons learned from this journey.
Great. So after this, what we learn on this journey. First, start simple and learn quickly. So we reuse actually as much as possible from the XGBoost model from the start. We started with the same data set, the same pre-processing pipeline, also using a scikit-learn. And then we tested incremental change by first testing offline with how Mihail explained, measuring the performance. And then when we had some positive, some signals, and testing online. So that's how we could test more than 50 iterations and end up launching more than 10 A/B tests in this 6 to 9 months. And that allows us to learn quickly. Second thing is you need to break it down in milestones. This is a big project, and breaking in milestone, which for us was first getting the technical parity, then getting the business parity, then improving, get business improvement. That helps the team to stay motivated, to celebrate the achievement, and also help to show progress to our stakeholders, saying, this is the goal that we had for this quarter, we achieved it, so we are going to the next one. And not like, where is the win directly. And finally, you can prepare and learn from others, but be ready for some bump on the road and be ready to adapt your problem. So for example, the people bouncing inform on next steps and where we had to go back to deviating from the plan, basically. So with that, that's it for us. So we are just 2 presenting, but actually it would have not been possible without the rest of the team, particularly Nikhil, our PM, Jui, Olivia, and Xingting, who made this possible. So yeah, we're also hiring in Berlin. Cool city, I swear. And looking forward for your questions.